of my YouTube channel. I am happy to meet you in the second part of state space analysis using phase variables video. So this is the continuation of my lecture 27. So the learning objectives are same as the previous learning objectives. The only difference is that we are going to obtain the state space representation of the system from the mathematical model if the system has got zeros also. That means it has got terms corresponding to derivative of input. Let us see with the help of an example. Nth order differential equation. So this equation is same, that is the left hand side of the equation is same as the left hand side of the equation that we have considered in the last video. Yn, a1, yn minus 1, a2, yn minus 2, etc. an minus 1, y dot, an y. This is same as the previous left hand side. The only thing is, in the last video, we have taken the right hand side as b into u, that's all. But here, we are taking the input also has got terms with derivatives. So, b naught um, b1 um minus 1, etc. bm minus 1 u dot plus bmu. To understand this still better, we will use some numbers instead of n and m. Always when we use some numbers instead of n and m or instead of some variables, it will be easy for us to analyze better. So n, m both are equal, we are considering. Y triple dot, yn means y triple dot n because n is 3. a1 y n minus 1 2, so a1 y dot double dot. a2 y n minus 2, so n minus 2 means 3 minus 2 1, so y dot plus next term is a3 y n minus 3, so a3 y, that's all. So last is a n y, so a3 y equal to b naught u, m is also 3, so triple dot plus b1 u double dot plus b2 u dot plus b3 u. Right. So if we take the Laplace transformation of this with 0 initial conditions, so we will get s cube y of s plus a1 s square y of s plus a2 s y of s plus a3 y of s equal to b naught s cube y of s plus b1 s square u of s plus b2 s u of s plus b3 u of s. So if we arrange that expression properly and write y of s by u of s, we can write b naught s cube plus b1 s square plus b2 s plus b3 divided by s cube plus a1 s square plus a2 s plus a3. So here we can find that numerator is also having s cube term, denominator is also having s cube term. That means numerator has got 3 roots, that means 3 zeros. Denominator has got 3 roots, that means the system has got 3 poles. So whenever the system has got zeros as well as poles, how to do it? If we can do it, then we can generalize for anything. So here there are a number of methods. So I have taken a very simple method wherein I am just decomposing this transfer function into 2. That means I am writing this as a cascaded combination of 2 transfer functions. That means y of s by u of s is written as y of s by x1 of s into x1 of s by u of s. x1 cancels. So here this b naught s cube plus b1 s square plus b2 s plus b3, the zeros terms alone I am assigning to this. Then 1 by s cube plus a1 s square plus a2 s plus a3. That means poles terms alone I am assigning to something. That means y of s by x1 of s is this, x1 of s by u of s is this. So here I am considering first this expression. From this expression we can write u of s by cross multiplication, u of s equal to x1 of s into this. That means this is u of s equal to s cube x1 of s plus a1 s square x1 of s plus a2 s x1 of s plus a3 x1 of s. So this is in s domain, therefore in time domain u of s is u, s cube x1 of s, that is we have to take inverse Laplace transformation, x1 triple dot, a1 x1 double dot plus a2 x1 dot plus a3 x1, that's all. So how to assign state variables in the same manner, but here we are not taking output as the state variable. We take x1 itself as a state variable, x1 dot is x2, x1 double dot is x3, x1 triple dot is x3 dot. because we are writing input in terms of x1. There is no output involved in this. Therefore, x1 dot is x2. x1 dot is x2. What is x2 dot? x2 dot is, that means this we have to differentiate. x1 double dot. What is x1 double dot? x3. That's all. Similarly, what is x3 dot? x1 triple dot. x1 double dot is x3, therefore x1 triple dot is x3 dot. That's all. So that is why x3 dot is this. Therefore, x3 dot we have to write in the proper form. Now, considering this expression, u is x1 triple dot is x3 dot plus a1 x1 double dot is x3, a2 x1 dot is x2, a3 x1. Therefore, from this x3 dot we can write, from this expression x3 dot is minus a3 x1 minus a2 x2 minus a1 x3 plus u. So, x1 dot equal to x2, x2 dot equal to x3, x3 dot equal to this. So, writing these three equations in vector matrix notation, we get this. This is same as what we have written for state space model using phase variables for transfer function without zeros. That is, state equations are same. See the last row, that a1, a2, a3, the coefficients of the left hand side, the coefficients of the left hand side we have written in the reverse order. Then this is the element just above the diagonal, they are 0, 1 and 1. Rest of the elements are 0. And the element corresponding to the last row in the B matrix is 1. Rest of the elements are 0. So this is the same form, right? This form is having the same or similarity, right? It has got similarity with respect to the state equations written for transfer function without zeros. However, the output is going to change because we have to consider the other transfer function, because we have decomposed this y of s into 2 now. Therefore, we have to consider this now. So, y by x1 of s is b0 s cube plus b1 s square plus b2s plus b3. Therefore, y of s is this. Therefore, y of s is b0 s cube x1 of s plus b1 s square s1 of s plus b2 x1 s x1 of s plus b3 x1 of s. So, if we take inverse Laplace transformation of this, y of s is y, s cube x1 of s will become x1 triple dot, s square x1 will become x1 double dot, s x1 will become x1 dot, x1 is x1. Therefore, instead of y equal to x1 in the transfer function without zeros, here we have y in terms of x1 and its derivatives. There y is simply x1. So here y is written in the form of x1 and its derivatives. We know x1 dot is nothing but x2, x1 double dot is x2, x1 triple dot, right? So x1 dot is x2, x1 double dot is x3, x1 triple dot is x3 dot. So we have to substitute the respective state equation, that's all. So x3 dot is, we have to substitute from this, right? So plus b1 x3, b2 x2, b3 x1. So the respective state equation is x3 dot, that's all. So if we write this in a proper form, x1 into b3 minus a3 b0, x2 into this plus x3 into this. That is, I am combining this x1 term with this x1, this x2 term with this x2, this x3 term with this x3. That's all. And you have u term. So state equations are there, output equation is there. That's all. So output is written not only using one state variable, it is written using 3 state variables and the input. This is where the difference lies as far as this form transfer function with zeros is considered, right? So compared to the transfer function without zeros. Let us understand with the help of a numerical example. So this is the transfer function. So construct state models. So we are not going to have 3 different state models. So construct, anyway, we will see other state models in the future videos. So we will see only one state model in this presentation. So the transfer function is there. So the transfer function is written in the form of decomposition. So zeros alone y of s by x1 of s, x1 by u is poles. That is how we have written, no? x1 by u poles, y by x1 is zeros. That's all, same thing. Right. So x1 by u we have to expand. So write u of s. So here we have to write in time domain. Therefore u is equal to x1 triple dot plus 4x1 double dot plus 3x1 dot. Same like this. Same like this. That's all. Nothing difference. Right. So state variables are assigned in the same way. x1 dot is x2, x1 double dot is x3, x1 triple dot is x3 dot. Again same thing. So I don't want to give the same explanation. Therefore by substituting a state variable, so e is equal to x3 dot plus 4x3 plus 3x2. So here again almost same as this. Right. So u is x3 dot 4x1 double dot is x3, x1 dot is x2. Right. So here we don't have x1 term in the right hand side. That's all. Why x1 term is not present means in the numerator, that is y of s by x1 of s by u of s and y of s by x1 of s. So if we consider this, that is when we take x1 of s by u of s, we don't have that x1 term. We get x1 dot because we have s term only here. There is no constant term here. Since there is no constant term, we don't get that x1 there. Whereas here, we got that constant term. We got this constant term now. This constant term we got. Whereas here, that constant term is not there. S into definitely the minimum term present is yes. That's all. So same way x3 dot is minus 3x2 minus 4x3 plus u. All this. Similarly, y of s by x1 of s is 10 into s plus 4. So if you write this in a proper form, 10s, so in 10s x1 of s plus 40 x1 of s. So in time domain y is equal to 10 x1 dot plus 40 x1. x1 dot is x2. Therefore, this is, so writing these three the state equations and output in the proper vector matrix notation form, we get this. So x1 dot x2 dot x3 dot. So 0 1 0 0 0 1. So minus 3 minus 4, x1 term is 0. 0 minus 3 minus 4. The last term of the matrix B is 1. Rest of the elements are 0. Here rest of the elements are 0. So if you compare this, so here if you expand this, this is s square plus 4s plus 3 into s. Therefore, s cube plus 4s square plus 3s. S cube plus 4s square plus 3s. So 4s square plus 3s plus constant term is 0. So 430 written in the reverse order. 430 written in the reverse order. So 034 with minus sign. That's all. Same thing. So y is 40x1 plus 10x2. That is 40x1 plus 10x2. Even we can compare this with this. That is b3 minus a3 b0. That is just by writing this. If we find out b3 minus a3 b0, all this, we will get this. That I leave it to the learner to try themselves. So these three, these two state equations and output equations put together is called state model, we know. So block diagram of the state model is given like this. So we know how to draw this. So we have to have u, x3 dot, we have to have x3, x2, x1, then output. So first we have to write for x3 dot. So there is no x1 term, only x2 and x3. So from x3 there is a term minus 4. Then for from x2 you have minus 3 added to u. Integrated is x3. That is on integration x2. That is on integration x1. So we need output 40 x1 plus 10 x2. So from x1 40, from x2 10 added y. That's all. So this is how we have to do the state space representation of the system using phase variables, whether you have zeros and poles or you have only poles without zeros. So I hope I have clarified how to do this. So watch this video and share this video with your friends and the learning community. In the next presentation, I will explain how to give the state space representation or how to obtain the state space representation using the canonical form or diagonal canonical form. So till I meet you in the next module, thank you and goodbye.